welcome back. So in this video our goal is to understand the connection between center of mass motion and linear momentum conservation law. So let's take a very simple example where these 2 point masses m1 and m2 are given and also their respective coordinates are given in x1, x2 and y1, y2. And the center of mass of these 2 point objects is simply defined as a linear combination of the respective coordinates. Here is the x coordinate of center of mass and the y coordinate of center of mass. If you see these equations closely, then you can see that the center of mass defined in this way lies on the line joining these two particles. Specifically, consider a very simple case where both masses are equal, and you can very easily see that center of mass lies exactly between this line joining these two masses. Now, if you differentiate these equations, you will see that the resultant equation give the velocity of center of mass. These are the component of x component of velocity and y component of center of mass velocity. And here I've written this is a vectorial form of the same equation. Now the interesting point here is that this quantity here in the numerator represents the momentum of the system. So for example, if mass m1 before the collision was having velocity v1 and mass m2 was having velocity v2, so this quantity represents the initial momentum of the system. And we have learned till now that if the momentum conservation is valid, then this quantity is not going to change. Momentum before and after the collision must be same. And it's very clear from this equation. And of course, if we assume that total mass of the system is constant, m1 plus m2, and which is true in all our examples or all of our simulations, which we shall see in future as well, it's very clear that the velocity of the center of mass must be a constant. And this fact is, I hope that it's clear that the velocity of center of mass is constant because this quantity, which is momentum, is conserved. So now let's turn our focus on a few more simulations from which we can easily visualize that how center of mass's velocity is constant before and after the collision. Now, after we have found the connection between momentum conservation law and center of mass motion, let's see a few examples of the same. So here again you have these two masses, and the center of mass lies exactly in the center, right, between these two masses. Now let me start. Watch closely. I'll reset. I'll reduce the time scale so that you can see it better. But basically you need to watch that the center of mass before the collision and after the collision moves with a constant uniform velocity. In this case you see that both the masses were moving with the same velocity in opposite direction, so the center of mass remains stationary. So before and after the collision, center of mass doesn't move, right? But in this case you see that center of mass is moving with the constant velocity, and even after the collision it moves with the constant velocity. Let's see more examples. Our previous example of collision between unequal masses. See the center of mass, it moves with a constant velocity. After the collision, momentum is conserved. Some more interesting examples, a series of collisions as we saw. Again, let's see the center of mass, where it is. It's somewhere here. And yeah, as expected, the center of mass doesn't move at all, right? Because it is conserved. In this example, the collision happens through the springs. So basically the collision process takes some more time than instant impact, as we saw in the previous examples. And basically again you will see that center of mass moves with a constant velocity at each instant of time. No matter what happens, it is moving with a constant velocity. And as we see these more complicated examples, it's just that the mechanism is becoming more complicated. You see, in this case, there are two springs which are connecting these three masses, and let's see the center of mass. And even now, no matter what, because of the fundamental idea that these the forces, the internal forces produced by the compression and expansion of the springs, or between the or when these masses collide, they are all internal forces, and according to Newton's third law, they cancel each other, and so the center of the momentum should be conserved, and henceforth we have already seen that the center of mass must be moving with a constant velocity. You see, the system is moving pretty complicatedly, right? It's not a very straightforward motion. If you see individual object, then definitely the momentum is not conserved for the individual object, but for the system as a whole, the momentum is conserved. Center of mass moves with a constant velocity. And as a continuation of these 1D air truck examples, as we see this a more complicated example, here's the center of mass. You will see that the motion will become quite involved. And at this moment you should be able to appreciate the idea of center of mass, because it becomes very complicated right now. Yeah, you see internal collisions, the springs are pushing or pulling each other, these objects, but for the entire system momentum is conserved, and it's verified clearly here by the constant motion of the center of mass. Now let's see some 2D examples, and to illustrate that the momentum conservation law is general and it's applicable in 2D or 3D. But okay, now you have a system of bodies. Again, they are resting on a frictionless surface, and we have this body. We'll give it an initial push, and let me toggle the center of mass. It's somewhere here, you can see, and let me start. What do you see? The center of mass still moves in a straight line. You can see all the bodies are moving in all directions with different velocities, but watch out the motion of center of mass. It doesn't know anything about what is happening around. It just moves in a straight line. Watch again, right? Move straight line. Another situation, I'll shoot these two masses, right, and you still watch that the center of mass will still be moving in a straight line. Yes, this time it's moving slowly in this direction because these bodies are spreading out in all the directions. So the center of mass moves relatively slowly, but still it moves in a straight line. Momentum is conserved. Now, so as we saw in all these simulations, the idea of momentum conservation, and I really hope that now after seeing these simulations, the idea of momentum conservation is clear, and also the interesting part that how center of mass motion is closely connected with momentum conservation law. I hope that that concept is also very clear. And in all these examples, we saw that there was no external force. Say, for example, in this case, friction wasn't present. You can say that gravity was there, but then it was balanced by the normal force, normal component of the force. And what happens to the center of mass motion when there is an external force? Well, those are also very interesting simulations. We can see it, but I guess right now we are running out of time. So for this time, we will leave this topic for now, and we'll see more simulations in future. Till then, thank you for watching.